I'm going to do a review regarding enzyme inhibition. First thing we need to notice is that we have many types. We have competitive, non-competitive, uncompetitive, mixed, and cooperative. So cooperative has a sigmoidal shape, and it's usually an example of this would be hemoglobin. When oxygen binds to one of the subunits, the next binding of the next oxygen molecule to the other subunit is actually better with higher affinity. We can also think of Km as the reciprocal of affinity. High Km means low affinity, and low Km means high Km means low affinity, and low Km means high affinity. Okay. So here we have these are called Lineweaver word plots. So what happens is we have the y-intercept and the x-intercept. So for the x-intercept, it's actually -1/km. The y-intercept is 1/Vmax. Km is a measure of affinity. Vmax is the measure of the velocity of the reaction. And it's kind of like similar to kcat. Okay, so we know that Km is the concentration that leads to half of the Vmax. Okay, so let's start with competitive inhibition. So for competitive inhibition, the first thing you need to memorize is that the Km goes up. If the Km goes up, that means lower affinity. Okay, and the Vmax stays the same. So the Vmax here, which is the y-intercept, stays the same, but the x-intercept, which is -1/km, is going to shift right because it's increasing. Okay, since it's increasing, we have closer to 0. Okay, so here what we notice is that for competitive inhibition, the inhibitor needs to bind at the active site, which prevents the substrate from binding to it. It does not bind to anywhere else but the active site. For non-competitive inhibition, the Vmax goes down, that means the velocity of the reaction goes down, but the Km stays the same. We represent it as this. The x-intercept is the same because the Km is the same, and the y-intercept goes up. You would think, wait a minute, why is it going up? Because remember, it's the reciprocal. It's 1/Vmax, so it's going to go higher. So this is the line with the inhibitor. So the Vmax is going to go down, therefore this shifts this way, and then the Km stays the same. So the x-intercept stays the same. Another important fact is that the inhibitor is going to bind to the enzyme at allosteric site. It does not bind at the active site. It binds at an allosteric site, and it does a 3D conformational change that prevents the substrate from binding to the enzyme and forming the product. It has the same affinity for the enzyme as the enzyme substrate complex. So you see here the enzyme with the substrate, and the inhibitor then binds and blocks the formation of the product. It has the same affinity for both, but in reality it's just the Vmax goes down, and then you can represent it in the Lineweaver plot as this equation. Okay, so for uncompetitive is both go down. Both the Km and the Vmax go down. You're like, wait a minute, the affinity is going up. Oh yeah, it's kind of strange. It's the Vmax goes down, but the affinity goes up. Okay, we represent it as parallel lines. Okay, because they're both going down. So you go from. Actually, this is supposed to be on top. Okay, so it's just gonna be parallel, and it's gonna go through there. Okay, just imagine that. It goes through there. Okay, so that would be uncompetitive. The Km and the Vmax both go down. For this particular one, which is uncompetitive, it definitely needs the enzyme substrate. So it needs the substrate bound to the enzyme, so after it binds to the enzyme, the inhibitor can bind in the allosteric site and prevent formation of product. Okay, now we have mixed competitive. As the name entails, it is mixed. Vmax is always going to go down though, and the Km can either go up or down. It can bind to the allosteric site if the Km is going down. So you have an inhibitor binding to the enzyme and the substrate, and the Km goes down, which means higher affinity. And or it can bind to the active site, similar to the competitive inhibitor, which bound to the active site. That's why this is called mixed, because it's similar, and then the Km will go up. But regardless of either case, the Vmax is always going to go down. You represent this as, it's weird, it's mixed, so you can either do both of them go down, right? The Vmax is always going to go down, so we can represent it as this, which is similar to this. I forgot to write the broken line there. So it's going to be parallel, or it can be similar, or it's going to go, Vmax goes down regardless, so it's still up, the y-intercept is still going to go above. But the x-intercept is going to shift right because the Km is going down. The Km is going up, the affinity. The Km is going, let me see, so the Km it's going to go up. So the Km is going to go up like the competitive inhibitor, so it's going to shift to the right. So that's fine. Right, another important point that we need to make is that non-competitive inhibition, you cannot remove that by adding more substrate. You can do it for this one, for competitive inhibitor. For the competitive inhibitor, you can add more substrate than the inhibitor because they're both competitively binding at the active site. So if we have more molecules of S, most likely there's not going to be enough space for I to bind because it's all taken by the S's. But for non-competitive inhibitor, regardless if you have a bunch of S's, the I can still bind behind it, and it can still block, do a conformational change so that then the S can no longer bind, and it's still the same case, even if you increase the substrate concentration, you're still going to have the inhibitor binding and preventing the reaction from going on. Okay, so that would be pretty much it. Another thing that I need to mention is that the other way of forming this graphing this is this way. The Vmax always has an asymptote going this way, so the Vmax is this one, so you just look at this side, that would be the Vmax. The Km you find by looking at the concentration that gives you half of the Vmax. So for example, if this is 10, then you look for 5 here, and then you look at the Km, let's say it's 1, so that would be the Km. If you have an inhibitor, let's say you have Km going up, that means the affinity goes down. So the Km, if it goes up, this is an example of the inhibition represented here because the Km is going to the right. It's shifting to the right, therefore it's increasing and lower affinity. The Vmax in this case can be represented by lowering it if we just move this downward like this. So this would be the line representing the inhibitor, this would be the original one. And that's pretty much it.